Okay. Welcome back to the Lafayette and Eureka people. Of course, I don't see any Eureka people on right now, so hopefully they will be joining us. Everything is, the notes and everything and the lectures are all posted on Blackboard for you to look at. And what we've covered in the last week has been the first three sections of Chapter 15, looking at functions of two variables and integrating. So please look over that material or read the textbook, whatever it is that you can do to get back up to speed. And then also there is, of course, there's homework due at the end of the week. And you guys, that's also posted and you should have that available to you. What we're going to cover today, or at least get started on, is section 15.4. And we're going to look at polar coordinates and how we can, for certain kinds of regions, polar coordinates really are a lot better than rectangular coordinates as far as trying to integrate. So it's double integrals using polar coordinates, in polar coordinates, integrals. All right. Okay. You know, up to now we've been integrating over regions that look kind of rectangular. But what if we wanted the region we wanted to integrate over say we wanted to integrate over R that looked like this, okay, here's our xy, and the region here is between two half circles. This would be x squared plus y squared equal 1, and then here is another half circle, x squared plus y squared, say, equal 4. And the region is here is what we would want to integrate over between those two half circles. Now, it is true that we could do it the way we had seen previously, where we could theoretically divide this region up into three type 1 regions, like right here, and right here, and right here, and do it that way. But we can do it a lot better, faster, rather than doing something like that. Okay, so let's take a little trip down memory lane for polar coordinates. So the relationship between polar coordinates and x and y . And the polar coordinates, we've got r and theta are the two variables here. And so the relationship between r and theta and x comma y, which are the rectangular coordinates. Okay, let's draw a little picture here. X and y. Theta, recall, is the angle that's made with the x-axis. And so if we have a point here, x comma y, first of all, it has a distance from the origin along this line, and that distance is r. And then we can use sine and cosine to represent the x and y. The x then would be r cosine of theta, the y would be r sine of theta. So x is equal to r cosine theta, y is equal to r sine theta. Also, r squared is equal to x squared plus y squared. That's from the Pythagorean theorem. And one other thing that we have is that the tangent of this angle theta is equal to y over x. Tangent of theta is equal to y over x. So these are four equations here that give us relationships between the two. And that should look vaguely familiar to you guys. All right. So if we want to describe this region up here in terms of polar coordinates, basically what we have is this. This first half circle, that represents r equaling 1. That's the radius of that circle there. And this other half circle, where x squared plus y squared is equal to 4, that represents r equaling 2, radius of 2. So in terms of polar coordinates, the above region R is the following. It's a set of r comma theta such that, first of all, r is between 1 and 2, and then theta for that region is just the half circle, so theta goes from 0 to pi. 0 less than theta less than pi. Okay. All right. This here, where we have r between two values and theta between two values, there's a name for that, and it's called a polar rectangle. So this is an example of a polar rectangle. Example of a polar rectangle. All right. In more general terms, a polar rectangle is going to be the following. In general, a polar rectangle is the set of points r comma theta such that r is between the numbers the positive numbers a and b, and theta is between the angles alpha and beta, say. Okay. All right. So let me just show you a little diagram here of this polar rectangle. It looks like a pie shape where part of the pie, say on the inside, has been removed, and so we have theta going from this angle alpha to this angle beta, and r starting, say, at this distance a and ending at that distance b. So everything in the gray there is the polar rectangle. Okay? All right. Now, what we want to do here is compute integrals over this polar rectangle. So we're going to start out just by subdividing it into little pieces like we did before with computing integrals over regular rectangles, okay? So to compute a double integral, okay, two integral signs over r of some function dA. What we do is we divide the radius into subintervals, and we divide the angle into subintervals. And we divide the angle theta into subintervals. And in addition, then, we get a bunch of little areas, and then we put a sample point right in the center of each area. So we picked a sample point, and we're going to pick it right in the middle, in the center of each area. And I've got a picture of this. Okay. So this is what we're talking about here. All right. So here's this area here between r equals a, r equals b, and so we divide up the radius into a bunch of different segments, and then we divide the angles into a bunch of different segments, and then in each one of these areas here, we select a sample point that's going to be right in the middle. So if this is, basically, if this is theta equals theta sub j, and this is theta equals theta sub j minus 1, the theta here in this, in that little area is the average of the two. It's right in the middle. As well as the r here, if this is r sub I and this is r sub I minus 1, the r here is also the average of the two r's. So it's right there in the middle. Okay. All right. Okay. Now, I want to mention one fact here before we go any further with this, and this is something that you may or may not remember from either geometry or trigonometry, this fact here. If we have a circle, and so we've got the center of the circle, and we have what's called a central angle. That means an angle coming out from the very center of the circle going to the circumference. And let's say that this angle is theta. The area of what looks like that piece of pie there, right here, the area is equal to 1/2 r squared times that angle theta. And of course, we're talking about the angle being measured in radians. So there's that fact there about the area of a circle that's cut out by a angle theta. All right. So with that little fact in mind, then, we can get the area of each one of these little sub-rectangles here. We can figure out what the area is of those rectangles, or what looks like rectangles. So the area then of each small, and I'll put this in quotes, rectangle, because they're not really exactly rectangles, we're going to call that area a delta A sub I, and it equals, if we look at this, let me just get this back here, it's really going to be the area of this piece of pie cut all the way here minus the area of this piece of pie right here. So what's left is that gray area after I subtract the smaller piece of pie from the bigger piece of pie. And I'm going to use this formula here. So the area of the bigger piece of pie is 1/2 r sub I squared delta theta. Delta theta is the angle that we're talking about, minus 1/2 r sub I minus 1, the smaller radius, squared times delta theta. And basically then we can do a little bit of algebra, which I'm going to omit. All right, it's no big deal, but I'm just going to admit it. What this ends up equaling is r sub I star delta r delta theta. where delta R is basically R sub I minus R sub I minus 1. And this Ri asterisk is the average of the two R's right there in the center. Okay. So we've got this formula here. So notice the formula for the area is basically we're multiplying our angle, a little bit of angle, by the average radius that goes out to that little sector, and then we're multiplying that by the delta R. So,
can you give what the R sub I star is?
okay. This is R sub I star is the value of R, which is here we have the for this rectangle, our inside R is R sub I minus 1. Our outer R is R sub I. Okay, so we have two R's here. This is the bigger one, and then this is the smaller one. This Ri sub I star is the average of those two R's. So it's basically right here, the R coordinate, we just add the two R's together and we multiply by 1/2. So it's the average of the two surrounding R's. Right? Okay. Where's that other little diagram here, which is helpful? Well, I'll get to this other diagram in just a second here. Okay, let me get another sheet here. So let me rewrite this. This delta AI, and we're talking about this area here, delta AI, is equal to that center R, the average of the R's, times delta R, the change in R, that's the change in R, times delta theta, which is the change in the angle theta. Let me keep that up there. What we're going to do next is we're going to do that what's called that Riemann sum, where we're going to add up we're going to want to integrate over all these small areas. So we do that Riemann sum with our functions that we're trying to integrate fxy. And we want to replace x with r cosine of theta, and we want to replace y with r sine of theta, all right, because we want to be using polar coordinates. So we get this, because we're summing over both, we're summing over two things. We're summing over r, and we're summing over theta. We're summing up all these things. We've got a summation over the r's. We also have a summation over the various thetas. So we have two summations involved here. We just say this is I equals 1 to m, some number m, j equals 1 to n. Now we're summing up the value of our function, and what we're replacing the x and y with r cosine and r sine. But we want to evaluate our function at that very center spot right there in the middle of that little rectangle. So we're evaluating it at, for x being Ri star cosine theta star, and then y would be Ri star sine theta star. Okay, that's center point, times the change in that small area there. And now what I'm going to do next is I'm going to replace the delta area, the change in the area, with this formula up here. So we now have a double summation, I equals 1 to m, thus j equals 1 to n, of our function evaluated over the center points there, Ri star sine theta star. And now I'm going to replace the delta area with how it can be represented in terms of our r and theta. So that's going to be Ri star delta r delta theta. Okay, so now it's all in terms of polar coordinates. And what we do here to figure out the integral is we take the limit as we get more and more of these rectangles, so we let m and n both go to infinity. Yeah, Jordan?
Should we put in the RJ there?
No, the r's are the same.
Then why
Because the thetas here are j. Sorry about that. The r's have a subscript of I, because it's the same r for both the x and the y. The angle theta has the summation over j. So r sub I, theta sub j. All right, so we take the limit as m and n go to infinity. And we get this. We now have the integral. So let me put an asterisk here about this integral formula that I'm going to put next. So the double integral over r of f xy dA is equal to this. Okay, theta goes from alpha to beta. R is going from A to B. We're going to put our function in terms of polar coordinates. So f is in terms of r cosine of theta, r sine of theta. And then we are going to replace dA with r dr d theta. So let me point out just a similarity here between this Riemann sum and the integral notation. The Riemann sum has a delta r and a delta theta. But when we do the limit as all these go to very, very small infinitesimal areas, we replace delta r with dr, delta theta with d theta. We replace our double summation signs with the double integral signs. Our function is here that we're integrating, and this is then being integrated over this polar rectangle. Theta is going from alpha to beta, and r is going from A to B. Okay. Probably the most important thing to remember about this formula is the following. Notice we do not just have dr d theta here. We have r times dr d theta. I can see that the biggest mistake on this would be to omit that R, when you're converting to polar coordinates here, is to omit that R right here. All right? So what I want to add here then is don't forget the additional R in the formula. And I've got a little diagram here that, where is that? Here. This kind of shows that the nitty-gritty of it here. Okay, here, this is that little stuff, rectangle type thing that we're integrating over, and we're calling that little piece delta dA. Well, we can look at what is its length and what is its width, because it's basically, when you get that small, it's basically like a rectangle. The length here is dr. The width here is our central, our angle theta, but notice as r goes out, that distance is increased proportional to the r, because it keeps going out further and further. So this length right here is r d theta. The other length is dr. So that becomes r dr d theta. dA gets replaced by r dr d theta. Right? All right, so another corny way to remember this, and don't throw anything at me, is okay, so anyway, this is such a barrel elapsed, all right? Hardy, hard, R, dr, all right? So we have R, dr, hardy, hard. Whatever it takes, I don't care, just don't forget the R, all right? Okay, now I think we're definitely due to do a just plain old example of this. So, example. Okay, evaluate double integral over R of 3x plus 4y squared dA, where R is the region in the upper half plane, so I'll make sure we understand what we're talking about there, bounded by the circle x squared plus y squared equal 1, and x squared plus y squared equal 4. Okay. In fact, this is exactly the area that we talked about at the very beginning that I gave as an example. Just want you to understand here, the upper half plane means we go everything from the x-axis on up. That is the upper half plane. So what we're talking about here is this very thing from the very start here. The upper half plane, so therefore we have half circles. The inner circle here is the x squared plus y squared equals 1. The outer half circle is x squared plus y squared equals 4. All right, so that's our region, our polar rectangle that we're integrating over. You have to be careful in carefully reading a problem that you don't somehow misunderstand the region that you're integrating over. All right. Okay, so let's see here. Okay, so let me just draw a picture. This is the region again. We've got this smaller half circle this bigger half circle. Now, okay, the circles are x squared plus y squared equals 1. Well, we know that x squared plus y squared is equal to r squared. So this is r squared equals 1. X squared plus y squared is equal to r squared is equal to 4. So therefore, r is equal to 1, take the square root, r is equal to 2. Okay, so we have to get our limits of integration for r and theta. For r and for theta. So r goes from 1 to 2. Theta goes from, because we're talking about just that upper half circle, theta goes from 0 to pi. Okay. So here's our integral here. Well, let's see, wait a minute now. We also need to rewrite 3x plus 4y squared, that's our function, in terms of polar coordinates, in terms of r and theta. So we're going to replace x with r cosine theta. So this is x is replaced with r. So we have 3 times x, that's going to be 3 times r cosine of theta, plus 4, y is equal to r sine theta, so y squared is r squared sine squared theta. So we have to make sure we rewrite our function accordingly. So this then is our integral. Theta goes from 0 to pi, r goes from 1 to 2, our function is 3r cosine theta plus 4r squared sine squared theta. And now we want to make sure we remember the extra r. R dr d theta. Okay, be sure you do that. In addition to your function, you have that extra thing. Okay, so let's evaluate this. So remember, we work from the inside out. So we're going to do this inside integral first. Now, I'm integrating with respect to r, so therefore that means the other variable is theta. That is treated as a constant. Right? So theta is a constant. All right. In fact, one thing I want to do with this thing, first of all, is I want to distribute this r with the 2 terms. So this is 3r squared cosine theta plus 4r to the third sine squared theta. Okay? And now let's get the antiderivatives of those 2 terms. Theta is a constant, so we have what? So that's going to just stick around as cosine of theta. 3r cubed is going to be 3r to the third divided by 3. So that's going to be r to the third cosine of theta. And then 4r to the third is going to be 4r to the fourth over 4. So that's going to be r to the fourth. And then we keep the sine squared theta, as it is. And then this is going to be evaluated from r equal 1 to r equal 2. And then we want to write our outside integral 0 to pi d theta. Okay? All right. So let's, what do we get here? This is basically going to be cosine of theta times 2 to the third minus 1 to the third. So that's going to be 8 minus 7, 8 minus 1. So we're going to end up with 7 cosine of theta. And then this is going to be r to the fourth. That's going to be 2 to the fourth, which is 16. minus 1 to the 4th, which is 1. So 16 minus 1 is 15, and then that's sine squared of theta. Okay, so that's so we've evaluated the inside integral, and now we go on to the outside one. All right. The first term is easy. The second term, we need to use an identity that we learned in Calc 2. And the identities, everyone know the identity of what sine squared of theta can be written as?
1/2.
Okay, 1/2. Well, you're on a roll with 1/2. Okay. It's a double angle thing. Okay. Well, okay. You said cosine 2 theta minus 1. It's actually 1 minus cosine of 2 theta, but you were close. And you know what? I think we better get reacquainted with that formula. So let me put a star here by that formula. And while I'm at it, let's just look at what is the cosine squared of theta. What is that? How does that look compared with what I just wrote? A plus sign, right? So it's 1/2 times 1 plus cosine of 2 theta. I'll put an asterisk by that. Kind of get that back in our tool bag, so to speak. All right, so this 15 sine squared of theta is going to become 15 times 1/2, 15 over 2 times 1 minus cosine of 2 theta. All right, or let me distribute it out. 15 over 2 minus 15 over 2 cosine of 2 theta. All right. All right, so now let's get the antiderivative. Antiderivative of 7 cosine of theta is the 7 sine of theta. And then now we go to our next term, which is 15 over 2. So that's going to be 15 over 2 times theta. That's our variable here. And then this last one here, we really don't want to go through all this U substitution turmoil to get this. We can get this without doing all that. What's going to be the antiderivative of minus 15 over 2 cosine of 2 theta? You went the wrong way. Sine, well, first will be minus. So the derivative, the antiderivative of minus cosine is a minus. Now, Jordan, you got rid of the 2 in the denominator. What you were really doing is taking the derivative. What do we do here with that 2 that's by that cosine of 2 theta? What do we do with that?
Bring it down, multiply by half.
We bring it down into the denominator, right? That's what you're saying? Yeah. So this, instead of being now 15 over 2, that 2 that's there, I bring it down, and that's 15 over 4. All right? It's just a quick way to do it without doing the formal U substitution. And then, of course, we have a sine of 2 theta. And, of course, if you check it, the derivative of this will give you what we started with. Okay, so we got the antiderivative. Now we have to evaluate the limits. Okay. And what are we going to come up with here for this value to start with this thing? Yeah. Yeah, 15 half times pi, but everything else goes to 0, right? Because the sine of pi is 0, sine of 2 pi is 0, sine of 0 is 0, sine of 0 is 0. That would be 0. The only thing that sticks around is 15 over 2 times pi, and that's our answer then. let me do something. You guys weren't here when I formally welcomed you back. Okay. All right. Okay. Oh, gosh. Yeah. You know, I hate Mondays because it's like, oh my God, we just get started and it's 5 more. Let me see here what. Well, let's see what we can do with this thing because I hate to quit. I hate to throw in the towel already. So if I keep talking, then I'm just defeating my purpose here. Let's see if we can at least get a start on this one here. And you do have to carefully read the problem. Find the volume of the solid that's bounded by the plane z equals to 0 and z equals 1 minus x squared minus y squared. All right, let's just kind of do a quick picture of this thing. Okay, so it's bounded by z equals 0, so that's the flat xy plane on the bottom. This is what I want to call the lower z. This here is going to be my upper z. Okay, when x and y are 0, z is equal to 1. And then as x and y get bigger in value, the z value decreases. So what we have here is this is actually called a paraboloid. It goes down like this, and then in the xy plane it goes around in a circle, and then it does this, of course, in the back of the xy plane like that. So this is the solid that we want to get the volume of. And the thing is, first of all, okay, this z equals 0, that's the xy plane. I need to figure out, well, what is the area here that I'm going to be integrating over? What is this area here? So I need to see where these two meet. In other words, I take z equals 0, z equals 1 minus x squared minus y squared, and what we get is, let me add x squared plus y squared to both sides. We get that they meet there in this circle of radius 1 on the xy plane. All right. So this here is a circle that forms on that xy plane. And this is the, shall we say, the boundary of my R that I'm integrating over. Okay, so therefore, if we want to look at this here on the xy plane, we have a circle of radius 1, and that is my R. Okay, so this is 1 here. So what are my, we've got to figure out what are our limits for R and for theta. Because we want to do, because it's circular, it just begs to be done using polar coordinates, right? So what are our limits for R and theta in our region R? R starts at 0 and it goes up to what value? No, that's theta. Theta goes from 0 to 2 pi. I'm talking about the radius, distance from 0. No, this is the circle of radius 1. So it goes to 1. So r goes from 0 to 1, radius 1, and of course theta goes all the way around. What Jordan says, it goes from 0 to 2 pi. All right. Now we need to get our, so what we're integrating is over 0 to 2 pi, from 0 to 1. Now our function is going to be, let me just put this down here. It's going to be the upper z minus the lower z, because we're wanting to get the volume. Well, the upper z is 1 minus x squared minus y squared. I want to get these in terms of polar coordinates. So 1 minus x squared plus y squared can be written as 1 minus parentheses x squared plus y squared, right? And so what would that be in polar coordinates? 1 minus r squared. Because r squared is equal to, remember, r squared is equal to x squared plus y squared. So 1 minus r squared, and of course my lower z is just 0, so I don't have to write that. So this is the function this is the vertical space that I'm integrating, and then don't forget it's r dr d theta, like that. Okay? Again, don't forget that extra r. So then this becomes basically a pretty simple integral to do. We just distribute our r, so we get 0 to 2 pi, 0 to 1 of r minus r cubed dr d theta, like that. And question, can I separate this as one integral times another integral? Remember that deal, a to b, c to d of f of x times g of y, dx dy. I could separate it as with the x and the y. So I could have a to b, gy, dy times c to d, fx, dx, like that, separated out. Well, really, I really don't even have a theta in here. This can be rewritten as 0 to 2 pi d theta, whatever I get from that, times 0 to 1 r minus r cubed dr. I can just separate it. So there's no theta stuck in there that I can't separate, that can't be separated out. What's the value of that 1 on the left, 0 to 2 pi d theta? Yeah, it's just 2 pi. But the antiderivative is just theta. This is just theta evaluated from 0 to 2 pi, which of course is just 2 pi. All right. And then the one on the right, we just get the antiderivative, which is r squared over 2 minus r to the 4th over 4. And we're evaluating that from 0 to 1. And that basically just gives us 1/2 minus 1/4, which is 1/4. And now we just multiply these two together, 2 pi times 1/4. And I get my answer is pi over 2. Okay. All right. So we'll finish this section up next time.